Welcome to another deep dive, and today we're tackling calculus. But not just the formulas and equations, although there will be some of that. We're going to uncover the story behind calculus, the how and why of it. It's a fascinating journey that really reshaped how we understand the world. Our main source for this deep dive is going to be the book 27 Leibniz El Calculo Infinitesimal.pdf.
We're talking centuries of math, from ancient counting to modern equations. What really gets me is how calculus came about from this need to solve real-world problems, not some theory.
All right, so let's set the scene. Picture 17th century Europe. So much change happening, politically, religiously, even militarily, but especially with science. It was an era unlike any before it. Scientific discovery at a breakneck pace.
Yeah, it was a huge shift. The ancient Greeks were all about theoretical science, but now people were getting practical, hands-on, and was changing everything. Think Galileo's law of falling bodies, or Kepler's laws of planetary motion, or Boyle's gas laws. Basically, the foundation for the Industrial Revolution was being laid right then and there.
So as scientific inquiry became more advanced, the math had to keep up. How did mathematicians deal with these increasingly complex problems back then? Did they just have to get bigger chalkboards and stronger coffee?
Well, they definitely had their work cut out for them. But the story of calculation goes way back. Like, think about early humans. Using their fingers as the first digital tools, they came up with some pretty ingenious methods to get beyond just basic counting.
Yeah, like that trick for multiplying by 9 using your fingers. You fold down the finger for whatever number you want to multiply by 9, then you just count the fingers on each side of the one you folded. The number of fingers on the left gives you the tens digit, and the number on the right is the units digit. Works like a charm.
Exactly. But as calculations got more complex, fingers and Roman numerals weren't cutting it. The need for better tools, well, it was pretty obvious.
And that's where we got the abacus, the OG calculating machine. It's mind-blowing that it was invented over 3,000 years ago and still used in some places into the 20th century.
It was a versatile tool. We have the Roman abacus, the Chinese swan pan, the Japanese soroban, even a Russian one called a chotu. They each had their own quirks, but the core idea was the same: beads on rods for units, tens, hundreds, and so on.
You can just imagine the resistance when the Indo-Arabic numbers started to spread through Europe. I mean, those abacus masters didn't want to give up their tool. There's even an illustration somewhere. It's like a calculator battle between an abacist and someone using those new Indo-Arabic numerals.
Classic case of pushback against new tech. But eventually, that Indo-Arabic system with that revolutionary concept of zero, well, it won out and changed math forever.
But even with this new system, people still wanted faster ways to deal with complex calculations. Which brings us to the brilliant John Napier, also called Napier.
He's famous for inventing logarithms in 1614. It was a game changer, especially for astronomy, streamlining all those calculations. Laplace, the French mathematician, even said logarithms basically doubled the lifespan of astronomers.
Wow, that's quite the endorsement. So how did logarithms work again? It's all a bit fuzzy from school.
They basically make it so you can turn multiplication into addition, division into subtraction, and powers into multiplication. Like a shortcut for all those calculations with exponents.
Right, exponents now I remember. Are there different types of logarithms? Base 10 and base e, something like that?
You got it. Base 10 are the common ones. They work well with their decimal system. But the natural logarithms with base e, well, they're super important for calculus and science in general. Even the abbreviation LN is a nod to Napier himself, stands for Logarithms Napierianos.
That's pretty cool, a little tribute right in the notation. So before logarithms, Napier also gave us Napier's rods, or Napier's bones.
Right, those rods were basically sets of numbered strips. They could turn multiplication and division problems into simpler addition or subtraction. Imagine multiplying a 3-digit number by a single-digit number. Arrange the rods side by side for the bigger number. Look at the row that corresponds to the single digit on each rod, add the numbers along the diagonals, and bam, you have the product.
It's amazing how driven people were to simplify these complex calculations.
For sure. And if we're talking simplification, we can't leave out William Oughtred and the slide rule from 1621. He built on logarithms, taking that simplification even further.
Ah, the slide rule. I remember seeing those in old movies, scientists sliding that strip back and forth.
Yep, they were pretty cool. It was basically a physical representation of logarithms, aligning the scales to do multiplication, division, even roots and powers.
There were different kinds, right? Linear and circular?
Yep, depended on the problem and what people preferred. But the main idea was the same: using logarithms to make complex calculations faster and easier. And the slide rule, it had a good run, centuries even, until those electronic calculators came along.
What a legacy. But we can't forget about some other pioneers of mechanical calculators. First up, Wilhelm Schickard and his calculating clock from 1623.
Schickard actually wanted to help his buddy Johannes Kepler with his astronomy calculations. They were pretty intense. In a letter to Kepler, Schickard even talked about how he imagined a machine that could calculate astronomical tables mechanically.
Sounds like a true friend. So what did this calculating clock look like?
It was this box-shaped device with gears that could handle addition and subtraction. It's thought to be the first mechanical calculator because it automated those basic operations using gears. It wasn't a clock for telling time or like a clockwork mechanism for doing math.
And even today, you can still find those additive calculators that are based on his ideas. He really laid the groundwork for what was to come.
Absolutely. And we can't forget Blaise Pascal and the Pascaline.
Ah, the Pascaline. Tell me more about that one.
Pascal was this brilliant French guy, mathematician and philosopher, created the Pascaline in 1642. It was a more advanced mechanical calculator, still using gears and dials, but it could do addition, subtraction, and even indirectly multiplication and division.
So a big step up from the calculating clock in terms of what it could handle.
Definitely. Pascal's design was a lot more sophisticated. The gears were way more intricate. Quite a feat of engineering back then.
And then there was Gottfried Wilhelm Leibniz, who built on Pascal's work with his stepped reckoner.
Leibniz took things even further in 1673. He incorporated this stepped drum mechanism. You could do direct multiplication and division so much faster and more efficient. He even showed it off to the Royal Society in London and ended up becoming a fellow.
It's amazing how this need for better calculation tools just spurred on all this innovation. But before we get into calculus itself, there are some key ideas and thinkers that we got to explore.
Absolutely. The story of calculus isn't just about the gadgets, it's about the ideas behind them. And to really understand that, we got to go back to the ancient Greeks.
Really, weren't they more focused on geometry than calculation?
True, but their focus on deductive reasoning and exploring areas and volumes laid the groundwork for everything that came later. They came up with ways to classify curves and prove mathematical statements from axioms.
So who are the Greek all-stars who really paved the way for calculus?
Two big ones, Diodorus and Archimedes. Diodorus lived around the 3rd century BC and was all about isoperimetric figures, figures with the same perimeter. He was exploring the relationship between a figure's area and its perimeter, basically early optimization problems.
So he was thinking about maximizing area or volume, concepts that we use in calculus today.
Exactly, he was laying the foundation for that. Then there's Archimedes, truly one of the greats. He's famous for his work on the method of exhaustion. It was a rigorous way to figure out areas and volumes by approximating them with polygons.
Oh, yeah, the method of exhaustion. So you take a shape like a circle and fit polygons inside and around it. And with each step, you get closer and closer to the actual area.
Precisely. It foreshadows the idea of limits, which is crucial in calculus. And of course, who can forget Archimedes and his eureka moment in the bath?
That's the one. The story goes that he got so excited about his discovery, he ran naked through the streets yelling, "Eureka!" Classic image of a scientist having a breakthrough. What problem was he trying to crack?
Well, he had to figure out if the king's crown was really made of pure gold or if it was a gold-silver alloy. And the principle of buoyancy, which says a body in a fluid experiences an upward force equal to the weight of the fluid it displaces, well, that was the key.
So even back then, math was solving real-world problems, sometimes with pretty high stakes.
Absolutely. And while Archimedes focused on specific problems, his methods paved the way for future mathematicians.
So this leads us to a shift from purely geometric approaches to more algebraic ones. Was there one person who really spearheaded this?
Muhammad ibn Musa al-Khwarizmi, a 9th century Persian mathematician, he's considered the father of algebra. His methods still relied on geometry, but he developed techniques for solving equations, laying the groundwork for algebra as its own branch of math.
It's amazing that both algorithm and algebra come from his name and his work.
Truly foundational. Then we have François Viet, a 16th century French mathematician. He revolutionized algebra by using letters to represent both parameters and variables in equations. This let him focus on general ways to solve equations instead of just specific problems.
So he moved algebra away from dealing with specific numbers and toward a more abstract, powerful system.
Exactly. That shift was essential for analytic geometry, which connected geometry and algebra.
Analytic geometry, that's where René Descartes and his famous coordinate system come in, right?
Right on. Analytic geometry, which was independently discovered by Pierre de Fermat and René Descartes, well, it revolutionized math. It provided a way to represent curves using equations.
So instead of just visualizing shapes geometrically, now they could describe them using equations, opening up a whole new world of possibilities.
Exactly. And the Cartesian coordinate system, named after Descartes, became the bedrock of analytic geometry. You have those two perpendicular axes, the x-axis and y-axis, and any point on the plane can be represented by its coordinates, x, y.
I think it's fascinating that Fermat's initial idea for a coordinate system was different from the one we use today. He used horizontal and oblique distances instead of perpendicular axes, and he didn't even use negative values.
True. It just goes to show that even groundbreaking ideas can change over time as different people refine them.
So now you have this powerful tool, analytic geometry, that lets you represent curves with equations. How did that lead to calculus?
We have to remember, calculus wasn't invented overnight. It evolved. And in the 17th century, a bunch of mathematicians were tackling problems and coming up with techniques that would contribute to its creation. They were getting really close to what we now know as calculus.
So who are some of these almost calculus pioneers?
One key figure was Bonaventura Cavalieri, an Italian mathematician and student of Galileo. In 1635, he published Geometria Indivisibilib Continuorum Nova Quadam Ratio Promota, which introduced his method of indivisibles.
Indivisible sounds kind of abstract. What are they?
Cavalieri's idea was that geometric figures were made up of an infinite number of infinitely small, indivisible parts. He saw areas as being made up of tons of parallel lines, and volumes as being made up of parallel planes.
So it's like slicing a shape into really, really thin slices.
Exactly. And by working with these indivisibles, Cavalieri came up with formulas for the areas and volumes of different shapes. Even curves defined by equations like x to the power of k, where k could be anything up to 9. He basically demonstrated what we now call the integral formula, but without the formal framework.
So he was basically doing integration, even though he didn't have the formal tools of calculus yet.
Precisely. He was setting the stage for what would come later. He also developed his famous principle. It states that if you have two planar or solid figures with the same height, and you slice them with parallel lines or planes at equal distances, if the sections always have the same ratio, then the areas or volumes of the whole figures also have that same ratio.
I'm trying to picture that. Can you give me an example?
Imagine two triangles, same base and height. Slice them horizontally at any level. The lengths of those slices will always have the same ratio. Cavalieri's principle says that means the areas of the two triangles have the same ratio, which we know is true.
Okay, that makes sense. So it's a way to compare areas or volumes without directly calculating them.
Exactly. And Cavalieri's work, even though some criticized its lack of rigorous proof, well, it inspired others to explore these ideas.
Like who? Give me some names.
Well, there's Gilles de Roberval, another big name at the time. He built on Cavalieri's work and used infinitesimal rectangles to approximate areas under curves. His method is a lot like what we call integration now.
So, divide the area under a curve into a bunch of tiny rectangles, add up their areas, and you get an approximation of the total area.
You got it. He used this method to find the area under a parabola, which is essentially the same as calculating the integral of x squared from 0 to 1.
Pretty impressive.
Right. Then there was John Wallis, an English mathematician who worked on infinitesimals. He's known for his work on the quadrature of the hyperbola, basically calculating the area under curves like y equals 1 divided by x.
Quadrature just means finding the area, especially for shapes with curves, right?
Yeah. And Wallis's methods, they might seem straightforward now, but he was getting important results that led to calculus.
Can you give me an example of how he thought about these problems?
Well, he found a way to figure out the area of a quarter of a circle by dividing it up into more and more lines and comparing it to a triangle and a square. It's hard to explain without a diagram, but it shows how he was thinking about areas in terms of these infinitely small parts.
So it seems like there was a lot of progress being made, but what were some of the big challenges that mathematicians were still facing?
One was understanding motion, especially that idea of instantaneous velocity. Imagine trying to figure out how fast something is going at a specific moment, only knowing the distance it traveled over time. Without the concept of limits, which wasn't fully developed then, it was a tough problem.
Right. Knowing your average speed on a road trip doesn't tell you exactly how fast you were going at any given time.
Exactly. And the reverse problem was tough, too. Given the acceleration over time, figure out the distance traveled and the velocity at any point. These problems really showed how we needed a more precise way to describe how things change over time.
Then there was the challenge of figuring out tangents to curves. that had uses in optics and mechanics.
Absolutely. Finding the tangent at a specific point was crucial to understand how light interacts with lenses or how things move. Roberval actually came up with a way to find tangents. Using this concept of a parallelogram of forces, he looked at the horizontal and vertical components of motion.
So he was using physics to solve a math problem.
Yep. It's a great example of how those fields can overlap and influence each other.
What about finding the maximum and minimum values of functions? That seems like it would be useful too.
Totally. Finding those maxima and minima is now called optimization, and it's used everywhere. Kepler actually used that concept to look at the shapes of wine barrels. He concluded that the cube holds the most volume for a given surface area.
So optimizing wine barrel design with early calculus, it pops up in the most unexpected places.
It really does. And of course, there was the challenge of measuring curves and solids, finding their lengths, calculating areas, and calculating volumes. This included things like rectifying curves, meaning finding their lengths, finding quadratures, which are areas, and finding cubatures, which are volumes.
It sounds like mathematicians were really pushing the limits of what they could measure.
They were. Francois Viet, the one who changed algebra with letters, he also found the first infinite product that approximated the value of pi.
Pi. That number really seems to be everywhere in math and physics.
It is.
Yeah.
And James Gregory, a Scottish mathematician, he came up with another formula for pi while trying to calculate the area of a circle analytically.
So it seems like everything was lining up for the invention of calculus. But we haven't even mentioned Newton and Leibniz yet.
They deserve their own spotlight. While a lot of mathematicians were doing important work, Newton and Leibniz were the ones who brought it all together. They were the ones who created a coherent system out of all these ideas.
So they were the ones who finally gave us calculus as we know it today.
Right. But their simultaneous discoveries led to one of the most famous controversies in science.
A mathematical rivalry? I want to hear all about this.
You'll have to wait for part 2. We'll dive into Newton's approach to calculus, all that drama surrounding its invention, and the impact it had on math.
Welcome back to our deep dive into calculus. Last time we talked about Cavalieri, Roberval, and Wallis, all working on things that would eventually become calculus.
Yeah, they were really setting the stage for a mathematical revolution.
And right at the heart of that revolution, as we mentioned before the break, are Isaac Newton and Gottfried Wilhelm Leibniz. Two giants of math whose simultaneous development of calculus caused a huge debate about who really deserved the credit.
It's a fascinating story, not just about their brilliance, but also about how messy scientific discoveries can be. Collaboration, rivalry, even national pride. It all played a part.
Okay, so let's start with Leibniz. We talked about his Step to Reckoner earlier, but what about his approach to calculus? What made it stand out?
Well, for Leibniz, it was all about differences in sums. He saw this fundamental connection between finding the area under a curve and finding tangents to curves. Two sides of the same coin, basically.
How did he connect those two ideas?
He started by dividing a curve into an infinite number of tiny rectangles, kind of like what Roberval was doing. But Leibniz took it further. He came up with the concept of infinitesimals to represent these tiny rectangles.
Infinitesimals. Okay, before we go on, remind me what those are again?
They were a pretty radical idea. Basically, quantities smaller than any number you can think of, but not actually zero. Like a rectangle so thin its width is almost nothing, but not quite zero.
Okay, I think I'm starting to get it, but I can imagine people back then had a hard time wrapping their heads around that.
Oh yeah, there was a lot of debate about infinitesimals. Some mathematicians weren't comfortable with the idea, but Leibniz, he was convinced they held the key to unlocking calculus.
And he was right. But working with those tiny things must have been tricky without a clear notation system.
Absolutely. Leibniz was a big believer in good notation. So he developed this meticulous system for representing these new concepts, and we still use it today.
Really? So what did he come up with?
Well, he gave us dx and die to show those infinitesimal changes in x and y.
Ah, yes. Those little symbols, they packed a lot of meaning.
Right. And then there's that iconic integral symbol to represent adding up an infinite number of those infinitesimal areas. Kind of looks like an elongated S, right? It's because it comes from summa, meaning sum.
It really captures that idea of adding up all those tiny pieces to get the whole area.
Exactly. Leibniz wasn't just figuring out the concepts, he was creating the language for calculus too.
So it wasn't just for convenience. The notation actually helped people understand and use those concepts.
It streamlined everything, expressing complex ideas clearly and making calculations more efficient.
Having the right tools for the job makes all the difference.
Absolutely. Speaking of which, Leibniz ran into some pretty tough problems, even with his new tools. One that really challenged him was the transcendental curve problem.
Transcendental curve problem sounds a bit scary. What was that all about?
It involved finding the area under curves that couldn't be defined by a simple algebraic equation.
Hmm.
Curves like sine waves or exponential curves. Imagine trying to calculate the area of a shape that's constantly changing and doesn't have a simple formula.
Like measuring something that's always moving.
Exactly. This problem forced Leibniz to come up with new ways to do integration. He realized he needed to expand the toolbox of calculus to handle these more complex curves.
He wasn't satisfied with just sticking with what he already had.
He was a true innovator, and in 1684 he published his first paper on calculus in Acta Eruditorum, a journal he helped create. That was the official debut of calculus to the world.
A big moment. So how did his ideas spread from there?
Well, Leibniz had some major supporters in Johann and Johann Bernoulli.
The Bernoulli brothers. I've heard their names, but I don't know much about them.
They were early fans of Leibniz's calculus, saw its potential, and worked hard to promote and develop it. They made the theory more rigorous and found tons of practical applications for it in physics, engineering, all sorts of fields.
So they weren't just mathematicians in an ivory tower. They were showing the world how to actually use calculus.
Right. They proved its power to solve real-world problems. They were finding lengths of curves, calculating curvatures, finding points of inflection, things that would have been incredibly difficult without calculus.
Hold on. Points of inflection. It's been a while. What are those again?
It's where the curvature of a curve changes sign. Like if a road curves left, then switches to curving right. That switch point is a point of inflection. Calculus gives you the tools to find and analyze those points.
So it's not just about abstract equations. It's about understanding how things change in the real world.
Exactly. And the Bernoullis were key in showing that to everyone.
Okay, I have to ask. Do you have any good Bernoulli brothers stories?
Well, Jacob Bernoulli was obsessed with the logarithmic spiral. He loved its mathematical properties so much that he wanted it engraved on his tombstone with the inscription Idem mutata resurgo, which means, though changed, I shall arise the same. But guess what? The stonemason messed up and engraved an Archimedean spiral instead.
Oh, no. A mathematical mishap. But it shows how passionate he was about his work.
It really does.
Yeah.
And it wasn't just the Bernoullis. Mathematicians all over Europe were excited about calculus. They started using it to solve problems in physics, engineering, astronomy, you name it.
So it quickly became a must-have tool for scientists and engineers.
Oh, yeah. And its influence only grew over time. We have Guillaume de l'Hôpital, who published the first calculus textbook in 1696 based on Johann Bernoulli's lectures. And there's a Leonhard Euler, who made huge contributions to calculus and its applications, and Joseph Louis Lagrange, who developed new methods for solving differential equations and advanced the calculus of variations.
Wow, it sounds like calculus really took off. But we still haven't talked about Newton's side of the story. How did his approach to calculus differ from Leibniz's?
That's where things get really interesting. Newton's path to calculus was closely tied to his work in physics. He wanted to understand those fundamental laws that govern the universe. So while Leibniz focused on the elegance of infinitesimals and notation, Newton had this more physical, intuitive approach.
That sounds like a story I definitely want to hear more about.
Well, buckle up, because in part 3, we'll dive into Newton's calculus, the controversy surrounding its invention, and the long-lasting impact of this rivalry on math.
Welcome back for the final part of our calculus deep dive. We've explored Leibniz's work with infinitesimals and his elegant notation, and now we're turning our attention to Isaac Newton, the other giant of calculus.
This is where it gets really exciting. Newton's journey to calculus is intertwined with his breakthroughs in physics and his drive to understand the laws of the universe.
So Leibniz was all about the mathematical elegance, while Newton was tackling the forces that shaped the cosmos.
Cool.
What a contrast.
It is. Newton's approach to calculus stemmed from his intuition about the physical world and his desire to explain everything around him. His calculus came from his investigations into things like motion, gravity, and light.
It's amazing how his quest to understand the universe led him to this groundbreaking math. So how did Newton's physics lead him to calculus?
It all started with his work on the laws of motion and universal gravitation. He was wrestling with some huge questions like how to describe the velocity and acceleration of objects. How do you calculate areas and volumes of curved shapes? How do you figure out the force of gravity between planets and stars? These were questions that had stumped people for centuries.
Those are some seriously big questions, the kind of questions that have driven scientific inquiry forever.
Exactly. And to answer them, Newton needed new math. He developed what he called the method of fluxions, which we now know as differential calculus.
Fluxions, that's a new one for me. What are they exactly?
Newton thought of mathematical quantities as always changing. always in motion, like
Yep.
a river constantly flowing. He called those changing quantities fluents, and their rates of change fluxions. So fluxions are essentially what we now call derivatives.
So if a curve represents a fluent, its fluxion would be the slope of the tangent line at any point on that curve.
Exactly. And Newton also came up with fluents of fluxions, which are basically what we call integrals now.
Yeah.
He saw the connection between those two concepts, finding the fluxion of a fluent and finding the fluent of a fluxion. That's what we call the fundamental theorem of calculus.
So both Newton and Leibniz independently discovered this fundamental theorem. Amazing how two brilliant minds working separately came to such a similar conclusion.
It really shows how math is this universal language. These truths are out there waiting to be discovered.
But this is where the story takes a turn. Newton came up with his method of fluxions in the 1660s, but didn't publish it until much later. Leibniz published his work on calculus in 1684. And that difference in timing ignited a huge controversy.
Oh, it did. The question of who truly invented calculus first, and whether Leibniz had maybe borrowed ideas from Newton, became a big debate that went on for generations. It was a clash of titans with intellectual rivalry and national pride mixed in.
Sounds like some serious drama, mathematicians taking sides, accusations flying around. It must have been quite a scene.
It was. English mathematicians were fiercely defending Newton, while continental mathematicians were all about Leibniz. It even became this battle between England and the rest of Europe, each side claiming victory. Unfortunately, this fight overshadowed the incredible work both Newton and Leibniz had done.
That's a shame. It's a reminder that even in science, emotions and rivalries can get in the way.
It's a good lesson to remember. But in the end, the truth comes out. Today, both Newton and Leibniz are recognized as independent inventors of calculus. They each made unique and valuable contributions to math, and their work has had a lasting impact on science.
It's fitting that such a powerful tool like calculus came from two extraordinary minds working independently. It shows just how deep and complex this field is.
It does. And their legacy continues in all the ways calculus shapes our world. From skyscrapers and airplanes to understanding how the human body works, calculus is essential for scientists, engineers, and so many others.
So even though there was a lot of controversy, we can be grateful that both Newton and Leibniz shared their discoveries. Their work truly changed history.
Absolutely. And there's an interesting twist to this story. The rivalry between Newton and Leibniz actually had a lasting impact on how math developed. English mathematicians kept using Newton's notation and methods, while continental mathematicians stuck with Leibniz's system.
So instead of working together and building on each other's ideas, the math community was split for a while.
Definitely a missed opportunity. But in the end, Leibniz's notation turned out to be more versatile and influential. It's what we use today, and is a big reason why calculus was adopted and developed further.
It's fascinating how something like notation can make such a difference. It shows how the language of math is just as important as the ideas themselves.
Exactly. Leibniz's notation gave people a clearer and more efficient way to work with calculus, which allowed the field to grow and reach its full potential.
What an incredible journey through the history of calculus. From early attempts to grasp numbers to the breakthroughs of Newton and Leibniz, we've seen how this powerful tool emerged from the need to solve real-world problems and evolved into the language of science.
It's a story of curiosity, ingenuity, and the pursuit of knowledge. It reminds us that discovery can be messy with twists and turns and rivalries, but in the end, it's that shared desire to understand that moves us forward.
As we wrap up our calculus deep dive, I'm struck by a sense of wonder. Wonder at the brilliant minds who shaped this field, wonder at how math can describe the universe, and wonder at how calculus continues to shape our world in ways we might not even realize.
It's a testament to Newton, Leibniz, and all those who came before them. They asked the tough questions, challenged the status quo, and pushed the boundaries of knowledge. They gave us a tool that changed how we see and interact with the world.
So the next time you see calculus, whether it's in a textbook, a research paper, or even in the design of a bridge or a smartphone, remember the amazing journey behind it. It's a reminder that even the most complex ideas often have humble beginnings, and that the pursuit of knowledge is a collaborative adventure across generations.
And who knows? Maybe inspired by this journey, one of our listeners will become the next Newton or Leibniz, pushing the boundaries of math and leaving their own mark on the world.
That's a great thought to end on. Thanks for joining us on this deep dive into calculus.